So let's talk about simulations of random processes. And using a computer to simulate a random process, that's one of my favorite applications of like these for loops, for example, where I can repeat the same process over and over again or repeat the same experiment over and over again. And in Math 9, there are two key questions we're going to discuss related to random processes. So key question number 1 is, given an outcome, how likely is it to occur? Okay, so for example, roll 3 dice, take the maximum of those 3 numbers. What's the probability that that maximum is at least 5? And question 2, what is the expected outcome? Okay, for example, roll 3 dice, take the maximum value of those 3 rolls, and what is the expected value of that? So expected value is the technical term, the term we use most often in math. Another way to think about it is average. Okay, they're really just 2 different terms for the same thing. At least how we're going to use it in Math 9, we're going to use expected value to mean average. And let me talk about how we can not find an exact answer to these questions using a computer, but how we can get estimates to these questions or to answers to these questions using a computer. So for question 1, let's talk about how we would investigate this. So let's start with, how about s equals 0? Okay, I'm using S to stand for success. Like, did the outcome we want to happen actually happen? And so then for experiment 1 to n, okay, and now here let's just say run the experiment. So we're going to run the experiment n total times. And if the outcome occurs, okay, then we're going to increase s by 1. So we're going to replace s with s plus 1. Okay, otherwise we don't have to do anything. So if this experiment was about dice rolls, then maybe this run experiment line would be replaced with something like choose a random integer from 1 to 6, or do that 3 times. And so then I've performed n total experiments, and s at the end of this process is going to say how often the outcome I was interested in occurred. And so then answer to question 1, probability. Well, probabilities, they're always numbers from 0 to 1. So how likely is it to occur? That really means what's the probability that this outcome occurs? And it's not exactly equal to this. This is my estimate. My estimate is number of successes divided by the number of experiments. And what your intuition should be is that the bigger n is, okay, then the better the estimate. Okay, and that's not a theorem, that's just some expectation you should have. So that's how we estimate procedure 1, is run the experiment n times, take number of successes divided by n, that's the probability. So if it happened 50 times out of 100, then the probability would be 0.5. So what about for this part 2? So it's very similar. Let's write t for total. And then for x from 1 to n. And then we're going to run the experiment. Okay, and then we're going to replace t, the total outcome of all of these experiments. Okay, we're going to add to that the new outcome. Okay, and again, what exactly I write here will depend on what the precise experiment is. And this run experiment line, maybe that's really something complicated. Maybe that takes about 15 lines, who knows? But this is just some shorthand for saying do whatever the random process is. And then here we had number of successes divided by number of experiments. It's going to be very similar here. Let's say, how about y for my expected outcome? That's going to be t divided by n. And you should have the exact same intuition as over here, that the more experiments you do, the closer you expect this to be to the actual expected value. And one of my favorite things about using computer simulations is that even if you have a pretty complicated procedure, if you take the number of experiments to be large enough, you see that this outcome, like for example, if you do this procedure 5 times in a row, if your value of n is big enough, these estimates are going to be very close to each other. And once you start seeing some kind of convergence, like these numbers are all very close to 3.6 or whatever, then that's a good hint that you've chosen a big enough value of n that you have an accurate estimate here for what the expected value is or for what the probability is back in question 1.